idea is, if suppose, have you done linear regression? What is linear regression in technical terms? It is looking at error, just like delta, gap between y and mx plus c. What is the gap? You look at that gap and you try to move the direction in the direction of where you minimize the error, and that's how you reach a slope where you're guaranteed that the m and b combination is such that your error is minimized. So what is the technique you use to reach there? I'm sure you've gone through that, right? What is the technique you use to reach the minimum in linear regression? It's called gradient descent. It's very similar to your, if you remember your grade 10 or grade 11 mathematics and calculus, when you are going to minimum, what do? You try to move based on differential of the sum, based on it going through a trough where second order differential becomes 0. So gradient descent is the basic technique wherever you want to perform minimization. What is the idea of minimization? That among many possible values, you start with the function and start moving towards the direction where your error is minimized. Even here we do the same thing. Only thing is, here the gradient descent is not necessarily guaranteed to lead to a global minimum. In linear regression, the surface is convex, because if you see what is a convex surface, if you take a surface like this, there is only one minimum, right? If you take a surface like this, there is two minimum, because it's not convex. What is convex? Any points you join on the polygon or on the graph, you make it fall within the graph. That is the notion of a convex surface. Whereas if you say, if you have something like this, if you join these two, this part is falling outside. So what is the idea of a convex diagram? It has only one minimum. Whereas in case of neural networks, unlike linear regression, we are not having the luxury of basically a global minimum. So you may get stuck in a local minimum. So what does gradient descent tell you? Gradient descent tells you that if you have to change the weight, the delta of the weight is dictated by whatever is the function, you have to take the derivative of that with respect to the function and derive the delta with respect to the function which you have. So the function means the activation function which you have chosen. If it's linear, then it's linear. If it is non-linear, you have to take the corresponding non-linear activation function. So whichever is the function, sigmoid or it's tan h or is it ReLU, depending upon that, you have to apply the corresponding partial differential equation of the delta with respect to that particular function. And that is what is going to dictate what is the difference between earlier W and the new W. So delta W is dictated by the function which is delta on the output layer as applied to the function which is transforming W to get the output function. That function will be different for different architectures. In one case you may choose sigmoid, in one case you may choose linear, in one case you may choose ReLU, in one case you may choose tan h. For each of them, the function which is going to define how the weight is to be updated, means delta W as applied to W to get the updated W will be defined by what is the corresponding output function. So delta E is dependent upon each of the error partially derived with respect to each of the W's in the previous layer. This is what will define how the W will change. Then You all know there is something called as learning rate, which dampens the process of reaching the minimum, right? So that's called as a learning rate. So what is the final delta W? Delta W is basically a learning rate times the partial derivative of whatever was the error, which is delta on output as compared with this, and you derive it with respect to each of the weights. That's how you get the delta W1, delta W2, delta W3, delta Wn. Each of them you compute as the delta with respect to each, and then you say that that's how you multiply with learning rate, and then you say that whatever is the original delta W, add the delta W, that's where you get the updated weights. Now this function is very much dependent upon the activation function and the actual function you are using to compute the next layer. So the partial differential ensures maximization of the slope to move to the nearest minimum. Why I said nearest minimum? Because unlike a convex surface like in the linear regression, we are not guaranteed of one global minimum. You will have maybe many local minimum. So you concentrate always on reaching the nearest local minimum with this. Now what is the gradient if you have a linear function or if you have sigmoid function? Each of the delta formula differs depending upon what activation function you are using. For example, if you have activation function which is sigmoid, 1 by 1 plus e to the power of minus a. So if you say delta W, it becomes sigma times y of 1 minus y times delta j times xij. This is basically for the sigmoid activation function. This one, same thing if it is suppose a ReLU, it will be a different function. Same thing if it is a linear, it will be different. So if it is linear, you remember what was the difference? Half of yi minus mxi plus b whole square. If you take that partial differential with respect to m, what was it? Minus of x, 1 minus x. Remember that? And for b it was just 1 minus x. So partial differential equation will depend upon what is the function which is there in your forward activation function. So here, this activation function is going to determine what is going to be the formula to derive delta W given an existing W. What is the change to the W you need to do is based on the activation function which is part of the network. So depending upon the activation function, the partial differential equation will give different formulas. But ultimately think about it like this. This is basically based on whatever is the function, we are going to take that and trying to create a slope such that it goes towards the minimum and it reaches the point where you are having a W which is stabilized. So what function you need to apply to delta W will be depending upon what is the activation function you are using and what the partial differential equation of that with respect to the corresponding W. So I don't expect you to know the full formula, but just keep in mind that if it is linear, it's going to be based on applying that on the linear equation. If it is going to be applied on sigmoid function, it's going to be applied on function here. But for the people who are interested in going to the next level of detail, you can work out the calculus here. This is the function. What is partial differential equation with respect to W for this equation? Same thing if it is a linear equation, it becomes this which you already know from the linear equation. It's very similar to what we did in linear equation. Same way if you have a different activation function, take that and do a partial differential equation with respect to that corresponding W. So what do you get at the end of it? For each W1, W2, W3, W4 at one layer, you get what should be the delta as applied to that. When you propagate the error which you got at output layer, you update the delta on each of the weights on the preceding layer. Now, once you get the preceding layer, again you compute the same thing on the previous layer. You update the weights there. Like that, you keep on continuing till you update the nodes immediately after input layer. There are weights connected to that, so you update weights of that also. So what backpropagation does is, ultimately, if you see at the highest level, it has computed delta, which is difference between the output expected and what output you got from the forward propagation, and taken the delta into account. I have updated weights along the path by this update rule, which is governed again purely by the each activation function at each node. And typically in a neural network, what you do is, you don't change activation function every node. Once you decide you're going to do sigmoid, it will be all sigmoid. Once you decide layer between layers, it's going to be ReLU, it's typically all layers will be connected with ReLU. It's not like every node will have its own activation function. Typically, activation function is a common thing across all the nodes. But once you backpropagated the error by updating W with delta W at each layer, all the way up to the input layer, you have done one pass. And then you are ready to work on the next input-output combination. Again, you will go through the same thing. Take the input data, run the forward pass with the updated weights. Your weights are updated, right? It's not the original random weights. You have put some element of updation there.